Well, thank you very much for having me. It's a pleasure to be here. I apologize for not being able to participate as much as I wanted in this workshop. The evening sessions didn't help much, unfortunately, the time difference. But here I am. So I'll be here today for the most part. I will talk about work that I did with Daniel Jafferis, and it was published earlier this year in September. Hopefully I'll have some time to talk about some related developments that are currently in progress with also Daniel, but also Jan de Boer. So the big picture idea is that what we would like to do is we would like to see the hologram from the inside. We would like to understand how to reconstruct the experience of an observer that lives in the bulk, and we'd like to do so from the perspective of the boundary CFT. Now, this switching of these reference frames is not something that we usually do in quantum mechanics, so the precise rules for how to do that are not clear. And of course, we won't address the problem in its entirety. We will address a simplified version of that problem in the context of ADS CFT. Now, this is not an academic question, or it's not just an academic question. It's motivated by the attempt to understand the black hole interior. The problem with black hole interior is probably known to all. If you try to probe the interior, in order to probe the interior of a black hole, perhaps a single-sided black hole formed from collapse, or a two-sided black hole like the one I'm showing in the figure, you will have to send something in. And if you send something in, it never comes out classically, or quantum mechanically, it will come out much, much later in a very scrambled form through the Hawking evaporation. So it's very difficult, and there are no known tools for reconstructing what happened to an infalling observer like the guy I'm drawing here in this figure. But of course, if one of you decides to get on a spaceship and go to the center of the galaxy and jump in the black hole, something will happen to you. And physics should be able to predict what will happen to you. So that's kind of the big question that we would like to, slowly make our way towards. How can we reconstruct the experience of an infalling observer past the horizon? And we will ask very simple questions for starters. For example, how much time did their clock measure until perhaps they hit the singularity, or until they met some other observer that jumped in earlier, or in this two-sided setup until they encountered some excitation I sent to them from the other side. A related question is a similar type of question is if they're, for example, did they encounter any particles along their way? If they're carrying a Geiger counter, did they measure any particles along the trajectory? And of course, a much more refined question is what are the operators that they can measure and manipulate? Namely, what is the representation of the operators that this guy has access to behind the horizon in the CFT? What are the CFT operators that this guy can access? So these are the general questions we would like to ask. And now, of course, we will address this, we will ask these questions in the context of ADS CFT, where we have a boundary description. We have a CFT that supposedly describes the entire system. But the CFT describes the system from the black hole from a distance, from the asymptotic boundary. And from that distance, the black hole looks like an ordinary thermal quantum system. It has some entropy, it has fast scrambling dynamics, it has unitary evaporation, and so on. And we have learned a lot about how to bridge this language of the CFT with the physics in the exterior of the black hole, or in these two cases, we have two CFTs and we have two exteriors, but we lack the tools for probing this interior region of the spacetime. And the approach we will take in order to address this question will be to switch reference frames, to understand how to switch reference frames to the frame of an infalling observer. But we would like to do that directly in the CFT. Of course, in the bulk, the switching of the reference frames, how to propagate operators along this word line is not a big mystery, because when you assume the bulk, you assume knowledge of all the fields in the bulk and the stress energy tensor, and therefore you can build the appropriate evolution operator along this trajectory. The problem, however, is that in ADS-CFT, we don't have access to the stress tensor in the bulk. The only thing we allow ourselves access to are the CFT degrees of freedom. So we would like to ask, what are the rules for constructing this proper time Hamiltonian, this operator that can take some operators outside here on the right exterior and propagate them along this word line in order to move them behind the black hole horizon. This is a question about how to reconstruct the interior operators in this kind of operational way. Choose an observer that you like, and then propagate these fields from the outside, propagate them with the proper time Hamiltonian of this observer. Then the question becomes, what are the rules for building this Hamiltonian? What is the definition of this proper time Hamiltonian in the CFT? Now, this is not, of course, we're not free to choose that Hamiltonian. It's something to be derived from some set of rules, and the identification of these rules is what we will try to make progress towards here. So, and I want to start with a little puzzle, a puzzling feature of this proper time Hamiltonian in this setup. So, let's this feature is present both in single-sided and two-sided black holes, like the one I'm drawing here, but it's more sharply described in the context of the two-sided black hole that I have already drawn. So this two-sided wormhole geometry is described microscopically, at least so we believe, by two conformal field theories, the CFT left and the CFT right. These two theories are holographic and they're copies of each other, but they are decoupled. Namely, the Hamiltonian does not couple the left CFT and the right CFT, but they start at this t equals 0 slice. They start in a very entangled state called the thermofield double state. So now I can introduce some sort of probe, that I will call an observer. I can introduce some sort of coherent wave packet here close to the right asymptotic boundary. And by the usual rules of ADS-CFT, I can introduce this probe by acting with an operator that is a right CFT operator. So I introduced this guy, but of course, because this CFT and this CFT are completely decoupled, no amount of dynamical evolution will mix this operator with the left CFT algebra, namely the commutator of the time of any amount of dynamical time evolution of this right CFT will commute with the entire algebra of the left, just by definition. However, according to this diagram at least, if I start with this operator and I propagate this operator in the reference frame of the infalling observer, if I propagate this guy along this word line, then after a finite proper time evolution, I find myself behind the horizon, and I can therefore receive signals from the left, which means that after a finite amount of proper time evolution of the right operator, this commutator with the left algebra has to be non-vanishing. Otherwise, I wouldn't be able to receive the signals. So this means that even though the two systems microscopically are not coupled to each other, they are only in an entangled state, somehow switching reference frames needs to introduce a coupling term between left and right in this proper time Hamiltonian that we're looking to define. So whatever rules we identify for switching into this internal reference frame, the frame of the infalling observer, will have to produce the right coupling terms in this proper time Hamiltonian. we're not free to choose those coupling terms. It has to be an output of the rules that we choose. So this is a little puzzle, how exactly the entanglement of the initial state translates into a coupling in the Hamiltonian of the infalling observer. So this is kind of a little puzzle. It was pointed out by Marolf and Wall back in the early days of the firewall debates. And it's also a puzzle that we will actually make some progress towards resolving. So the big question is, what are the rules for constructing this Hamiltonian? What are the first principle rules for switching to this internal perspective? And this is, I'm motivated using black holes, but I could also ask the same question in ordinary bulk reconstruction without black holes, namely. Of course, there in ordinary bulk reconstruction, there are many available techniques already in place. HKLL reconstruction, modular flow reconstruction, PetchMap, but all of them require as input the bulk geometry. At some point, we always input information about the solution, the classical background solution in the bulk. So one would like to ask, is there a way of extracting information about the bulk and about the experience of an observer propagating and exploring this bulk directly in the CFT without, in some kind of universal way, without making reference to an explicit solution in the bulk? So this is what this is another way of motivating the search for a first principles approach, a CFT principled approach for constructing this proper time evolution along an observer's trajectory. Okay, this is the motivation, and let me now explain the setup, how we are going to make progress towards this question. So we want to introduce some sort of probe that will serve as our observer. But we don't, in general, introducing an actual observer is of course a very complicated business, but we're not trying to construct human beings. What we want is a simple, universal, and well-behaved classical probe. And what's better than a black hole? So a black hole will be our notion of an observer. There's many reasons why a black hole is a good observer, a good probe. First of all, it's classical. Second, it has a universal response to particle detection. When a particle crosses paths with a black hole, it just absorbs it and it gets fatter. So this is kind of the response of our detector to a measurement of a particle. Also, it's very simple to introduce a black hole directly in the CFT without making reference to the bulk. So here's how we're going to do this. So the left part over here is the system, the holographic system that we want to explore. And we will introduce a black hole into that system in the following way. We will consider our system and a reference system, and we will entangle them in the thermofield double state. This creates in our universe a static black hole sitting at the center of ADS, entangled with an external reference. But of course, this is not a very interesting spacetime. So what we're going to do is the following. So we will start with this thermofield double state, and we will act on it with a unitary that acts only on the system side. And the role of this unitary is twofold. So first, we will act with an ADS translation in order to move the black hole away from the center of ADS, to shift it out towards the asymptotic ADS boundary, in order to kind of get it out of the way. And then the rest of the unitary, its role is to generate whatever classical background I would like to propagate, I would like to explore. So I first take the black hole out towards the asymptotic boundary, and then I act with a unitary that creates the whatever space-time geometry I want to explore. So far, I have this state between system and reference, and I have acted with a translation let me call it P rho for some large rho. And then I acted with the system unitary that curves my background. And then I time evolve with the dynamical Hamiltonian. And this gives me a state psi of T. And this state psi describes the evolution of my black hole in that spacetime. So this will be our setup. For as long as the black hole is smaller than the features of the spacetime I created with my unitary, then it will approximately propagate along the word line of the ideal observer of general relativity, just by the equivalence principle. Okay, so this is the notion of observer I will use. A little black hole that I'm introducing somewhere near the boundary. I act with the unitary to generate the curvature of space-time and excite my bulk fields, and then I let the system evolve, and the black hole will start moving in the bulk according to its equations of motion. That's the setup. Now, a very quick, yes.
Do you require the same picture in this reference side?
So I will not. So the reference, the reference system, I don't touch it. The role of the reference is a method for tagging the frame of my black hole. It helps me know where the black hole is, essentially. It won't play any other significant role. You can think of it as, well, we can discuss exactly what the physical meaning of this reference system is. But at this level, in this formalism, it's simply a very convenient way of kind of tagging, of marking my observer, of the frame of my black hole. Perhaps more conceptually, you can think of, every observer has a set of microstates. So the reference state is some sort of proxy for the internal structure of the observer themselves, which you don't include in the description of the universe. We can discuss this more in the discussion later, but for now, this is a convenient machine for keeping track of where my black hole is, of the frame of my black hole. So all the operations I'm writing here are operations on the system side, the system being the universe I want to explore.
Okay, thank you.
Sure. And feel free to ask questions. You don't have to wait until the end. It's actually probably better this way. So just a very quick comment. I introduced my black hole using this thermofield double state, which means that I'm describing a black hole on my system side in the canonical ensemble. And you're probably familiar with the fact that a canonical ensemble describes very big black holes. Namely, it can only describe black holes that are whose radius is the ADS radius. So they are cosmological side black holes, not exactly what we mean by probes, usually. So that is okay. An ADS black hole is an LADS black hole is a probe if the features of the spacetime are much bigger than LADS. But you can also do better. You can also define a microcanonical version of the thermofield double state, which is essentially identical to the thermofield double, but you include this kind of envelope function, which kind of projects this entangled state on a more narrow energy window. This type of microcanonical black holes can be made much smaller than LADS. Namely, small black holes dominate the microcanonical ensemble for a black hole radii that go to 0 as I take n to be large. So we can make these observers much, much smaller. There are some other subtleties there, but the size of the observer doesn't seem to be an important restriction in this formalism. However, I will continue using these thermofield double observers for convenience and clarity, and because we haven't fully worked out the situation with these microcanonical thermofield double guys. It just I just wanted to mention that it doesn't seem to be a big restriction to go beyond big probes that I'm using in this talk. There doesn't seem to be a fundamental restriction. Okay, so I introduced my probe. It's a black hole entangled with a reference. And I would like to learn how to propagate degrees of freedom along the trajectory of my black hole. But I don't want to, there's no well-defined notion of propagating operators that are far from the black hole along the word line. You know, there's no preferred slicing of the bulk. However, so that's why I will focus on operators that are very close to my black hole in what I will call the atmosphere. So there are some degrees of freedom very near the black hole, which I will call the atmosphere operators. It is these guys that make up, if you will, my observer's lab. And it's this operator's evolution that I'm interested in describing. In particular, I'm interested in the unitary that relates this atmosphere operator algebra at some initial time and some final time. So I start somewhere, let's say I introduce my black hole somewhere near the boundary, it propagates through the spacetime, and then at some later point, I kind of regain control of my black hole, and it's over here. So I have this algebra of operators in the atmosphere here. I have this algebra of operators in the atmosphere, in the original atmosphere. There's a unitary V, and that relates these algebras, and this is precisely the proper time evolution that I'm interested in. So, of course, the point of the talk is to describe how to construct this unitary from first principles. This is the goal. A small technical comment that will be important later on is that remember that these are operators that are defined in a gravitational system, and therefore I have to specify their dressing and how exactly I locate them in the bulk. So I will dress them to the black hole horizon, in particular to the black hole, to the apparent horizon of the black hole. So if this is my black hole in the original slice, I simply label these fields phi with respect to the geodesic distance from the apparent horizon on that slice and their angular location, you know, along the sphere, the horizon, the angular coordinates on the horizon. Of course, if matter falls in, this will cause the black hole to get bigger. So the horizon location gets shifted, and therefore the operators, the atmosphere operators after the infalling matter will be dressed to the new horizon. So they will be also shifted, and this will be an important feature later on. Okay, so what is it, what generates, oops, I'm sorry. So what generates this proper time evolution V? How can I start with these original atmosphere fields and move them along this word line in order to obtain the final operators? What are the rules for constructing this directly in the CFT? Well, roughly speaking, the whole point will be to look at the modular clock, the evolution generated by the modular Hamiltonian on the system side. The modular Hamiltonian I'm referring to is the following. Remember that we had this state psi of t, which was this time evolution of the unitary acting on the thermofield double between the system and the reference. So now what I want to do is I want to trace out the reference. And because of the entanglement between system and reference, I get a reduced density matrix for the system. The modular Hamiltonian is simply minus the logarithm of this reduced density matrix. And in the state that I have, this is exactly the form of the modular Hamiltonian. Is unitarily equivalent to the dynamical Hamiltonian. So roughly speaking, the point will be that proper time is generated by this modular Hamiltonian plus some corrections that I will discuss in some detail. So the way to see why this modular clock seems to be related to the proper time clock is the following. Essentially, it's because the modular Hamiltonian near the horizon of the black hole generates approximately this Rindler symmetry, the Schwarzschild boost symmetry, close to the horizon. The way to see this is the following. A more appropriate and general definition of this modular operator is in terms of this as this KMS operator. Namely, you define the exponential of minus k as being the operator whose matrix elements are given by the overlap of these two states, but where these operators are exchanged. This, of course, is a KMS operation. And the point is that if I go very close to the black hole, if these phi's are in the atmosphere of my black hole, very near the horizon, then to some approximation, this atmosphere is in local thermal equilibrium. And the role of this thermal circle is played by the weak rotation of the Schwarzschild time, of the local time-like Killing vector. This means that the modular Hamiltonian, its action on the atmosphere fields, is equivalent to the action of the Schwarzschild, of the generator of the Schwarzschild time. So K acts in the atmosphere as the generator of Schwarzschild time. So to see it in pictures, if I go close to the black hole, there's this local time-like Killing isometry, and it's generated approximately by the modular Hamiltonian, at least as long as I can assume that the atmosphere is in local thermal equilibrium. Now, the reason why now this local Schwarzschild time should be associated to the proper time of the observer is because is because the Schwarzschild time actually does map to the proper time of the ideal observer in the following sense. Imagine for the time being that I didn't have the black hole in my spacetime. I instead had an ideal observer propagating in it. If I focus in a little neighborhood of this observer, the spacetime looks approximately flat. So this means that there's some local Killing vectors that form the Poincare algebra. One of those vectors preserves the word line of the observer, and I call it the generator of proper time. Now, when I replace this ideal observer with the physical probe, my black hole, I can think of this process as the following cutting and pasting procedure. I choose a large enough neighborhood of my ideal word line, this tube over here, and I remove the inside, and I replace it with the black hole and its surrounding spacetime. But in order to glue this black hole spacetime to the exterior spacetime, I have to do this smoothly at the boundary. And the two conditions are that the size of the transverse sphere is continuous along this boundary. And the other one is that the local Killing vector of the original spacetime gets glued to the local Killing vector, time-like Killing vector of the new interior spacetime. So the Schwarzschild clock gets glued to the proper time clock of the original observer. And therefore we conclude that the modular Hamiltonian is, or the modular time, if you will, let's call it tau, is correlated to the proper time. So this is a very quick and simple argument for kind of an illustration mostly of why you should expect this modular Hamiltonian to be, or the modular clock, the modular time, to be related to the proper time of the probe. However, this is not an exact statement. There are corrections to that statement. An assumption in deriving this correspondence was that the atmosphere was in thermal equilibrium. But if there are particles flying around in my spacetime and they kind of fall in the black hole or pass through the atmosphere, they will disturb that thermal equilibrium. And when these particles, and when this happens, the modular Hamiltonian not only doesn't correspond to the proper time evolution that we talk about in general relativity, but it is in fact a non-local operator. So there are corrections to that statement. And I would like to now talk about these corrections. And the observation is the following. So this v of h is precisely this proper time evolution that I'm referring to, and I just simply took the logarithm of it here to kind of talk about the generator of it. So this part is the modular Hamiltonian that we already talked about, that modular time is generated by that proper time is generated by the modular time. There could be other zero modes related to whether the black hole got rotated along the way and so on. They're not very important. The important corrections are these two, and let me talk a little bit about them. As I said, when particles fall in the black hole, they disturb the thermal equilibrium that we used in order to relate the proper time to the modular time. However, the important observation is that the black hole behaves as a dissipative system. Namely, these fluctuations, these perturbations away from thermal equilibrium that I caused with these infalling particles, they dissipate because their evolution in time is controlled by the quasi-normal modes. So if I wait for longer than a thermal time after the last particle fell in, its imprint it has actually decayed exponentially in proper time, and therefore all of these little disturbances can be neglected to leading order because they're exponentially small. So all these disturbances of thermal equilibrium matter at intermediate times, but they're only transient effects. So if I wait a little bit longer, a thermal time longer, then they go away. There is, however, one effect that persists. And the effect is the fact that the black hole got bigger because it absorbed the new particles. So the key observation, the second key observation that Daniel and I made was that this other persistent correction can be included in also a universal way by including this operator G, which we call the modular scrambling mode. And it's defined to be an eigen operator of the modular Hamiltonian with an eigenvalue minus 2 pi I. The 2 pi comes from some conventional normalization of this of the modular Hamiltonian. The important thing to notice here is that this is an eigen operator with an imaginary eigenvalue, and therefore when I evolve it with the modular Hamiltonian, it grows exponentially in time. We call it the modular scrambling mode or the modular chaos mode because this weight that you see here, this 2 pi, describes the fastest possible growth, the highest modular weight that can appear in this expansion here. So there is a bound on how quickly these contributions can grow in modular time, and this bound is set by precisely this exponent. So the piece that I'm adding here to describe the growth of the horizon is precisely this maximal chaos mode. The coefficient of this maximal chaos mode describes, it depends on the energy distribution of the infalling matter. So I will explain why this is, how to understand this maximal scrambling mode in just 1 second. But just to reiterate the claim is that when no particles fall in my black hole, then the previous argument this explains how proper time corresponds to modular time, at least near the horizon. When there is particles flying around and they fall in the black hole, the two persistent effects, the proper time evolution in this case is again modular evolution corrected by some amount of scrambling mode flow, which takes into account the growth of the horizon. So let me explain now where this last part comes from, where this correction comes from. Well, as I said, the black hole can work as, essentially operates as a particle detector. And the response of this detector is that every time a particle falls in, the black hole gets bigger. So now let's try to formalize this a little bit more carefully. So we start at some initial time, t equals 0, and I act with some unitary that will introduce some particles in the spacetime that are supposed to fall in my probe black hole. So these are the particles. This red wiggly line is the particles that I introduce with my unitary. Well, what we learned from, from 't Hooft back in the days, and more recently from Schenker and Stanford, is that if I want to glue that spacetime of the bigger black hole onto the spacetime of the thinner black hole, I have to do that by including a relative null shift between the location of the causal horizons. This relative null shift depends on the distribution of the energy of this infalling shockwave, and it's called it's what we refer to as the Shapiro delays. But remember that what we want to refer to as the proper time evolution is the evolution of the initial atmosphere fields in time while preserving the distance from the apparent horizon. This means that after this infalling matter has been absorbed by the black hole, because of the shift of the horizon, this atmosphere operators also get shifted so that they preserve the distance from the new location of the horizon. Namely, this guy is originally dressed to the RT surface, whereas this guy is dressed to the new shifted horizon. So proper time evolution is supposed to move me along this trajectory that I had drawn here in red. The point, however, is that this is actually related this is related to the modular flow of this particle by a shift. And let me explain now where this comes from. The point is that this red line is the proper time evolution as expected by the bulk geometry, but this green line is the modular evolution, what the modular evolution does. So to kind of correct the modular flow in order to obtain the proper time flow, I have to shift that particle along this null direction by an amount equal to the Shapiro delays. The way to see this is by simply take the overlap of the modular float operator acting on my state and the actual proper time operator, proper time evolved operator acting on the state. And noticing that this overlap is an OTOC, is an out of time order correlation function. And it's out of time order because this phi over here is up here and this uj is down here. And we know that OTOCs are described by this 2-point function, including a relative null shift, which is precisely this, this Shapiro delay I was referring to earlier. So if I want to, in order to reconstruct the proper time flow, modular flow alone is not sufficient because it will move me in this direction. I have to correct it by including this null shift. This is what this calculation here instructs me to do. In this particular case, this null shift is generated by this average null energy operator along this horizon. And the property of this guy is that its commutator with the Hamiltonian is precisely, I'm sorry, this is P minus, is precisely satisfying this algebra with the Hamiltonian because of the local Poincare symmetry very close to the horizon. The Hamiltonian generates the boost, and this guy generates shifts, and therefore this follows from the local Poincare algebra. So in the general case of a moving black hole, the role of this scrambling mode that I was referring to earlier, this maximal chaos mode, is the analog of this null shift in the frame of the moving black hole. Putting everything together, what I try to explain is that This proper time evolution is generated in general by modular flow corrected by an amount of scrambling mode flow whose role is to account for the shift of the horizon as a result of the infalling matter. Of course, there are other corrections which are relevant for intermediate times, but they decay, and that's why we can neglect them for certain questions. So what have I said so far? What I said so far is the following. If you start your system in some state and you introduce your black hole in the system as a probe, then you can do the following. Introduce the black hole, let it evolve, and then let it evolve, go through the system, and then regain access to it at some later time. If you have access to your system at the initial and the final time, then by the unitary, this abstract black box unitary that relates the initial atmosphere operators to the final atmosphere operators, you can extract two pieces of information about the experience of the observer as it passed through the spacetime. The coefficient of the modular Hamiltonian of in this generator measures the proper time, and the coefficient of the scrambling mode, the maximal chaos mode in this generator, measures the infalling distribution of the particles that your detector absorbed along the way. So two pieces of the experience of this bulk observer can be reconstructed by looking at this chaos mode and the modular Hamiltonian mode in this generator. What I want you to notice is that nowhere here did I use any property of the bulk. I used bulk reasoning to derive this result, but this final formula does not make reference to any bulk physics. I did not use, let's say, the metric in which my operator propagated in. The only operators that appear here is, in this expansion, is the modular Hamiltonian of my probe, which I obtained after tracing out the reference, and the modular chaos mode, which is defined with reference to the modular Hamiltonian as the guy with this maximal modular weight. So both of these operators do not require as an input for their definition the bulk solution. So that's why I am referring to the universality of this proposal. The ability to extract information about what happened to your observer without referring to an explicit bulk solution. Okay, so this has been relatively abstract. You can actually do this explicitly in an example in ADS. You can play around. I don't have time to describe this, but the whole point is that you can show that this unitary that moves you along a trajectory in ADS can in fact be expressed as can in fact be generated by the modular Hamiltonian, and the coefficient that appears from the calculation is in fact the proper time you would compute geometrically. And you can do this for accelerated trajectories as well. You know, you can, so it works for any observer in ADS, that's the point. In my remaining perhaps 5 minutes, I'm not sure how much longer you wanna listen to me ramble. I would like to get back now to this original puzzle that I talked about. The puzzle of how do we understand this situation of an observer introduced from the right, falling in a two-sided black hole. How can we understand their ability to receive signals from the left, even though they were made out of right CFT operators? So again, we start with this two-sided CFT setup, decoupled CFTs in this thermally entangled state, the thermal field double. And now we want to introduce an observer on the right. But now let's use the framework that I advocated for. Namely, we want to take some subsystem of the right CFT and entangle it to the reference, to a reference. So let's do this a little bit abstractly first, and then we'll talk about an explicit example. So how would I do this? Well, we have the thermal field double between the left and the right, and we start the reference in some kind of reference state that doesn't really matter. To introduce my observer, I have to act with some unitary, which couples the right and the reference. In this way, I have entangled this particular modes of the right CFT to the corresponding modes of the reference system. So I created this entangled state between my right observer and my reference without ever touching the left. I did not do anything to the left. This unitary doesn't see the left. Now, according to what I said, modulo the corrections that I described, proper time evolution in the observer's frame should be generated by the modular evolution. What modular evolution? Well, I have to take this state and trace out the reference and obtain a modular Hamiltonian on my system and evolve operators with this modular Hamiltonian in order to propagate some operator over here along this trajectory. Well, the crucial observation here, and the thing that we found quite interesting, is that because of the pre-existing entanglement of the thermal field double, the observer's modular flow couples left and right. This means that the set of rules that I described, and I argue they work in situations where we have nice control over all the quantities we talk about. The rules that I described for switching reference frames, for constructing the Hamiltonian in the reference frame of the internal observer, naturally contain this coupling between left and right CFTs when the original left-right CFT state is entangled entangled enough. So in this sense, I would say that this set of rules that I described to you just do not suffer from this commutator puzzle, this Marolf wall puzzle that I described in the beginning. Simply because if you now take this atmosphere operator and evolve it with this modular flow, it eventually becomes a two-sided guy, and there is absolutely no puzzle about why you can receive signals from the other side. I just want to take 1 minute to kind of give you an explicit kind of toy example of how it seems to work in general. And this is the following. Instead of talking about a pro-black hole falling into a bigger black hole, into a bigger two-sided black hole, let's talk about a pro-black hole falling into a Rindler horizon. So the way we do that is we start with the black hole at the center of ADS, entangled with a reference using in the thermal field double state. And then I do exactly what I said in the beginning. I act with the translation. So originally my black hole is over here. I act with the translation to move the black hole out towards the boundary by applying an ADS translation on the thermal field double. The modular Hamiltonian of my black hole then is this. But now I want to what I want to do is I want to kind of view the bulk spacetime in terms of two Rindler wedges, with the black hole contained entirely on the right wedge. So I split my universe into two Rindler wedges. The Rindler boosts play the role of the dynamical Hamiltonians on the two sides. And if I express this modular Hamiltonian in terms of this Rindler wedge, you can see that this modular operator K is a sum of this boost, which is the difference between the boost on the right and the boost on the left, and a sum of these two translation operators along the horizons. The average null energy translations, the average null energy operators, which induce translations along these Rindler horizons. These, of course, are two-sided guys that couple right and left. So if I take an operator out here, in the original slice, and I evolve it with a modular Hamiltonian, then its late time, at sufficiently late times, this will look like this, where the important thing to notice is that this operator gets translated along this left-moving null direction, and therefore it inevitably at some point it crosses the right horizon. So it is in this sense that the rules that I described, the identification of modular flow with the proper time flow in the frame of the observer, naturally kind of resolves this puzzle about how can I receive signals from the left. So I think I'll stop here. I had a few slides describing a remaining puzzle, and it's the part that is currently ongoing work with Jan de Boer and Daniel Jafferys. But I don't think I think I should stop here. I'll just end with a comment that what I described to you is a first step towards understanding time in a quantum gravitational system. The notion of time I described, this internal notion, the construction of the clock of an internal observer, is a natural notion of emergent time. And it's the one that emerges from the entanglement of the observer with the environment. So an interesting question to ask for the future is whether this somehow is part of a bigger story that is more universal and more general and applies to other systems describing gravitational quantum gravity. And I'll end here. Thank you for your attention.
Okay, thanks to the speaker. Any questions or comments?
I have a naive question. So at some stage you were claiming that the result is fairly universal, doesn't depend on any property of the bulk. Mm-hmm. So I was wondering, what if I replace a small black hole by a heavy particle, and would the result be the same?
Yeah, so good. Well, ultimately you would want to do something like this, right? So, right. So good. So let's see. So there are various issues with particles, and I do not want to claim that you can take this formula and simply generalize it to an arbitrary probe. That's because in order to derive this formula, we used what helps us is the universal features of the black hole itself. Namely, the fact that the modular Hamiltonian generates this boost symmetry close to the black hole horizon, and the fact that the way it responds, the way the black hole responds to any particle it emits is universal and can be encoded in this, can be accounted for by this chaos mode. So this was very important in deriving this formula. So the universality of this formula partly has to do with the universal features of the probe I'm using. So that's why I said in the beginning that I will not be able to give you a general framework for switching to the reference frame of an electron, let's say, because I don't even know if that makes any sense really. But we will find an idealized probe that can see aspects of the spacetime, which we can use to see aspects of the spacetime in a universal way. So assuming the probe, namely assuming that you will use a black hole for probing the spacetime, the result is universal in that you don't have to input any knowledge of the bulk, the ambient spacetime in which your black hole moves. So it's universality in this sense. It's not universality in the probe you use. It's universality in the ambient spacetime that your probe will move in.
Okay.
There's a question in the chat. Does this formula work in lower dimensional case, for example, 3D and 2D? So okay, let's see. In 2D, there's actually a chance that you can do better. There is a chance in which you can actually, in fact, use particles to propagate, to kind of apply this method for moving in behind black hole horizons. It's something that I didn't mention, but it's ongoing work with Isaac Kim and Junyu Liu, where we are trying to see how we would construct precisely that that little setup here of the observer falling in a two-sided black hole, how we would explicitly implement this procedure for constructing an observer, introducing an observer on the right and kind of exploring the internal black hole in this SYK context. So there's a chance here that you can do better and you can have a microscopic derivation of all these things. And in 3D, there are some issues about black holes in 3D and whether you can actually have an extra black hole that you introduce in the space-time of a bigger black hole just because of the weird properties of the BDZ. So I'm not entirely sure if you can actually introduce a black hole probe in the BDZ spacetime. That's an interesting question that I haven't settled. I haven't really convinced myself it's possible. Maybe it is, maybe it's not. Happy to discuss about this.
Well, in fact, I have a little puzzle related to the previous question. The probe black hole should radiate gravitational wave. Does that have influence on the proper time?
You mean if I introduce if the black hole propagates in a space-time that contains a gravitational wave?
Yeah.
Yeah. So yes. So the point, the claim at least, is that the proper time that you measure with the coefficient. Let's go to this formula. If you go to the right, so whatever spacetime you have, for as long as this spacetime is sufficiently semi-classical, it's not like some superposition of very distinct geometries where, you know, probably this formula breaks down, but also probably the question of the proper time doesn't make sense. If the spacetime is semi-classical, like for example, some gravitational wave propagating on top of pure ADS, then the claim would be that if you take this unitary that relates the early and late atmosphere fields and you decompose them in terms of the definite modular Hamiltonian modes, namely the scrambling mode, the zero modes, and everything else, then this formula would just simply apply in that case as well, with the proper time being the appropriate proper time in the space-time with a gravitational wave. Now, have I done this calculation myself to be 100% sure that this is how it works? The answer is no. I've only done the calculation of a black hole propagating in ADS and giving it little kicks that are artificial kicks that I'm introducing by hand. I believe that so while I haven't done the calculation in an actual propagating gravitational wave geometry, the fact that this calculation works in this kind of example of a black hole propagating and getting a sequence of kicks that mimic acceleration, I think it guarantees that it works on all weakly curved weak curvature perturbations of pure ADS. And then the hope is that it works more generally, but again, you know, you have to. It's a hope but not a proof.
Thank you. Any other questions? No? Then let's thank the speaker again.
Thanks for having me.
Thank you.
I'll stop sharing my screen now so that you guys can proceed. Great.
All right.
Yeah, let me share my screen.
Yeah, our next speaker is Xinan Zhou from Princeton, and he will talk about all holographic 4-point correlators in maximally symmetric CFTs. Let's welcome.
Okay, so thanks. So let me start by first thanking the organizers for putting together this very nice workshop and for the invitation to give this talk. Today I'm going to talk about some recent progress on computing holographic correlators, and the talk today is based on the two recent papers with Fernando Alday, and it's also part of a modern program started with Leonardo Rastelli in these papers. So I will begin with some very quick and brief review of ADS CFT. So everybody knows that string theory or M theory on an ADS time sphere is due to some superconformal field theory that lives on the boundary of the space. And the correspondence gives the dictionary for observables on both sides. And the most basic entry is that the CFT correlators are mapped to the scatter amplitudes in the bulk of ADS. And this correspondence becomes most tractable when we look at the limit where the bulk theory is a weakly coupled supergravity theory. And so in today's talk, we are going to focus on computing these CFT correlators holographically. And let me first offer a few motivations. So the first motivation is that we can use the weakly coupled bulk dual to learn about physics of the strong coupling. So we know that quantities not protected by supersymmetry are very difficult to compute using QFT methods. And this is especially true if the theory we are interested in does not even have a Lagrange description, for example, for these 2,0 series in 6D. And then ADS CFT will be the only way to make progress. The second point is that we can also go in the other direction. So we can go from trees to loops to learn about quantum gravity. So at this point, a direct loop level calculation in the bulk is very difficult and impossible. But this is also not really necessary because we can use some very well developed bootstrap techniques to just compute loop correlators, loop corrections by after inputting tree level data. So it works roughly like this diagram. It can be viewed as some ADS version of the unitarity method in flat space. So these holographic correlators, they provide a very concrete setup for studying ADS gravity at quantum level. And it can also go beyond just two derivative supergravity, and we can also consider higher derivative corrections coming from string theory or M theory. And this can be done by combining this ADS unitarity method with other techniques. So studying these correlators also provides precision tests for the ADS CFT correspondence. The last motivation has to do with the connection with scattering in flat space. So we know in flat space, the scattering amplitudes, they have very rich mathematical structures. So a very natural question is if we can find similar mathematical structures in these scattering amplitudes in ADS. And we know that in flat space, when we study when we study amplitudes, we can learn a lot about the symmetries of the theory, which are not really obvious from the Lagrangian description. So we can ask what kind of symmetry properties we can also learn by studying these holographic correlators about symmetries of ADS series. And finally, in flat space, there are very efficient techniques to compute scattering amplitudes. And it will be very interesting to explore if similar methods can also be generalized to computing ADS scattering amplitudes. So those are the motivations. So now I'll be a bit more specific. So let's first start with the question of what kind of theories we are looking at. So in this talk, I'm going to focus on theories with the maximum amount of supersymmetry. So that is, we have 16 Poincare supercharges. And I require this so that we have the maximal amount of analytic power. So this means that if we look at d greater than 2, then we are left with 3 options. So the first is we have 2B supergravity on ADS 5 times 5, and this is just due to 4D n equals 4 sigma mils. And we can also consider 11-dimensional supergravity compactified either on ADS 4 times 7 or ADS 7 times 4. And they are due to 3D n equals 8 ABJM or 60 2,0 theory. In today's talk, I'm not going to talk about the 2D case because the 2D correlators, they have some unique features which do not generalize to higher D. But here I just want to quickly mention that there has been some recent progress in studying the case of ADS 3 times D3 times Q3. So now we have specified these theories, so we can ask what kind of operators or particles we are looking at. So in all these 3 theories, we start with some higher dimensional field, and then we perform Kaluza-Klein reduction on the internal sphere, and that gives us infinite many KQ modes, which are organized into superconform multiplets. So the operators we are going to scatter are the superprimaries of these superconform multiplets, and they're due to some scalar fields in the ADS. So here is a precise dictionary. So on the ADS side, we're looking at the so-called 1/2 BPS operators. So they preserve half of the supersymmetry. And in the bulk, they are due to some scalar field. These operators, they are labeled by some integer k, and they carry k indices. So these indices, they transform in the rank k symmetric traceless representation of the asymmetric group, which is SOQ plus 1. This asymmetry group in the bulk is just the isometry group of the internal sphere. And this integer k is just the number of angular momentum on the internal sphere. And because these operators, they're protected and their conformal dimensions are proportional to this integer k with some coefficient epsilon that's related to the space dimension d. And in the bulk, it corresponds to some protected squared mass. So there are infinitely many of these multiplets, but the one we are most familiar with is the k equals 2 multiplet. That is the stress tensor multiplet. And of course, each multiplet contains finitely many superconformal descendants, but I'm not going to be very explicit about them at this point. So we are looking at the correlation functions of these half BPS operators. So let me mention that 2-point and 3-point functions, they're trivial because they're essentially just fixed by symmetries. The interesting case is they start from 4-point functions, and that's going to be the target of this talk. We are going to look at such 4-point functions with arbitrary K1, K2, K3, K4, and there are infinitely many of these guys. So now let me briefly review how these objects were computed historically. So the traditional method of computing these objects to use brute force diametrical expansion in ADS. And the procedure is very familiar to what we do in flat space. So the first step is just to figure out the Feynman rules in ADS. And that includes finding the propagators and vertices. So here we look at 4-point functions, so we need both cubic and quadratic. And we also need to know how to do the integral. Once we have this information for a particular 4-point function, we need to enumerate all the diagrams and then evaluate these diagrams one by one. And finally, we add up the diagrams and try to simplify it. So this may seem very straightforward, but it's actually not. So on the right, I'm showing you the inputs you need to do the calculation. So here, this giant mass is all the quartic vertices for ADS 5 times 5, which are needed for computing a genetic 4-point function. And as you can see, it takes 15 pages. So this traditional approach is really a recipe for disasters. So because of this, there have been a very few results in the literature, and most of them in the case. There was one example for ADS7, but there was no result for ADS4. And actually, in that case, people even they couldn't even evaluate these individual diagrams. So it's fair to say that there was a very little understanding about the structure of these correlators, and people didn't really understand what are the underlying organizing principles. Recently, there has been some progress using some bootstrap ideas. And one lesson we've learned about these holographic correlators is that they have very rigid structures. Namely, they can just be fixed by using symmetries and consistency conditions. So that leads to a number of methods which have enormous advantage over the traditional method, but they also have some shortcomings. So I'm going to briefly review these methods. But before I do that, let me first discuss a bit about the superconformal kinematics. So we have these 1/2 BPS operators. They carry some indices, which are kind of annoying. And there's a convenient way to make them disappear, which is to contract them with some null vectors. So null here means that t times t is 0. So this requirement automatically projects this representation to the symmetric traceless representation. And so now all the indices are gone, and then the 4-point function becomes a function not only just of the spacetime coordinates x, but also these coordinates for the asymmetry part. Now we can use asymmetry, conformal symmetry and asymmetry to extract a kinematic factor. And then the 4-point is written as the function of the cross ratios. So here U and V are the familiar cross ratios for conformal symmetry. And we also have defined sigma and tau for the asymmetry part. So here we have a number, curly E. This E is called extremality. It is sort of a measure of how complicated this correlator is. So this E is determined by the external weights. And from the definition, one can show that this curly G is a polynomial in sigma and tau. And the degree of the polynomial is given by extremality. Now, in this step, I've only used the bosonic part of the superconformal group. There are also constraints from the fermionic generators of the superconformal group. And those are going to impose extra conditions known as the superconformal word identities. So to write these identities down, we need to introduce a change of variables. So here I'm going to write U and V in terms of Z and Z bar. And similarly, I'm going to write sigma and tau as alpha and alpha bar. And then the superconformal word identity tells me that the correlator on this special slice needs to satisfy this differential relation. The second piece of technology I need to introduce is the so-called mating representation formalism. The idea is very simple. So we start with this correlator, and then we do 2 inverse mating transformations with respect to U and V. The dual variables are S and T, and these are the analog of Mandelson variables in flat space. And we also introduced another variable U to make things more symmetric. And they need to satisfy the relation that the sum of ST and U is the sum of external conformal dimensions. So you can think of the right-hand side as the sum of squared mass, if that's the flat space case. There's also a factor of gamma functions. It's just there to capture these double trace operators, which are universally present in large M correlators. So all the information goes from curly G to curly M, which is called the mating amplitude. So we can immediately see that this is a good idea by looking at individual Witten diagrams. So if you look at a contact interaction where this quadratic vertex has 2 L derivatives, then we find that the mating amplitude is just polynomial of SNT of degree L. Furthermore, we can look at an exchange diagram in the S channel. We find the amplitude is very simple. It's sum over simple poles with polynomial residuals, and this also is a regular piece. These poles, they form a semi-infinite series. They start from the conformal twist of the exchange operators, and you have some descendants. Here, let me also point out that this regular piece is not really uniquely defined, because we can choose different cubic vertices that are equivalent on shell, but they can modify this amplitude by some additional contact terms. And genetically, this expression has infinitely many poles, but if the spectrum is special, for example, for ADS5 and ADS7, then you find the infinite series of poles can truncate into finitely many terms. And this truncation is a consistency requirement from the 1/n expansion. But this does not happen for ADS4 because it has a different kind of spectrum. So these are all the ingredients I need to introduce and review these bootstrap methods. So the first is what we call a position space method. It's really a proof of principle. So it's very much similar to the traditional approach, but the difference is that so we are going to write down an onset in terms of just all the diagrams that can appear. But we are not going to specify the contribution of each diagram, because that is the hard part. So we would know these contributions if we know the precise vertices, but we saw that these vertices took 15 pages. So we are instead going to just leave these quotients unfixed and then impose the superconformal word identities to fix these quotients. So it turns out all the quotients can be fixed. So that tells us that this idea of bootstrap really works. And of course, this method is not a very good method, because if we want to consider more complicated correlators, there are going to be a lot of diagrams. So then the second method actually is a lot more elegant, which we call the algebraic bootstrap method. So the idea is that we are going to rephrase this task of computing correlators as solving a bootstrap problem in mailing space. So to do that, we first need to solve the superconformal word identities in position space, and the solution takes the following form. So we have a protected part, which can be computed in zero coupling, and then there is another part that captures the dynamics. And the second piece has the form of some differential operator, which is completely specified by symmetries, acting on some edge, which is called the reduced correlator. And then we want to translate this identity into mailing space. And we can argue that the protected part doesn't contribute, so we can just ignore that. And on the left-hand side, we have already defined the mailing amplitude M. And similarly, we are going to define a reduced mailing amplitude M tilde for H. And that gives us some identity between these two, because we can translate the differential operator as a difference operator in mailing space. So this condition takes care of the superconformal symmetry, but we can also impose conditions on analytic structures, both symmetry and asymptotic behavior. And those conditions, they together formulate a very constraining algebraic bootstrap problem. And then we just need to solve this problem. So we managed to solve this problem for all correlators for ADS5 and ADS5. So that's very nice. So this approach has clear advantages. So first of all, we don't need to compute any diagrams, and we can deal with all the correlators at the same time. We can also generalize this approach to the ADS7 case, but it also has some problems because in this approach, we are focusing on this reduced mailing amplitude. The downside of that is that we don't really have much of a intuition about the analytic structure of M tilde. So that makes it difficult to formulate general ansatz, for example, for the ADS7 case. So we can do this case by case, but we don't really have a general answer. And this approach is also problematic for ADS4, because in that case, this differential operator D is non-local, and we don't know how to interpret that in mailing space. And finally, there's another approach in mailing space, which basically is the first one, but we do everything in mailing space, and there's some nice trick to implement superconfirmed word identities there. And the advantage is that we can deal with all dimensions now. We can even compute correlators in AES4, but just as method one, this works case by case, so it's hard to get a general answer. So basically, that's the status so far. So we developed these methods using Bootstrap ideas, and we can compute correlators in all these three models, but the only case which we managed to solve in general is the case of ADS5. And so the goal of today's talk is to go beyond that and want to solve the other two more difficult cases, namely ADS7 and ADS4. And we are also going to try to see if we can find some universality in these different theories. So to do that, so we first need to realize that, so previously in the ADS5 story, this reduced amplitude actually played a very important role, but we need to realize that it might not be so useful in general. So for example, this notion of reduced amplitude does not even exist for ADS4. And also it does not really have a physical meaning by itself. Only the full amplitude has a physical meaning. So that seems to tell us that we need to focus on the full amplitude, which is of course more complicated, but we can try to look for certain limits which simplify the answer. So here is an idea that is inspired by what happens in flat space. So in flat space, the notion of maximally helicity violating is very important. So we are going to define something similar to this called maximally asymmetry violating. So we started by associating each operator with some polarization vector T for the asymmetry part. So we can define the following U-channel MRV limit by setting the polarization of operator 1 and operator 3 to be equal. And in terms of the cross ratios, that means sigma equals to 0 and tau equals to 1. So I'm going to call this a slice of the full amplitude, the MRV amplitude. So now let's see how this limit is useful. So here I'm giving you the simplest 4-point function for ADS7 times S4. So these are the 4-point functions of stress tensor multiplets. And as you can already see, this simplest correlator is already quite complicated because we have this huge numerator here. But magic happens if we take this MRV limit. So if we set sigma equal to 0 and tau equals to 1, we find this complicated expression becomes a very simple expression that can fit into one line. And in this answer, here are two features I want to point out. The first is that this MRV amplitude does not have any singularity in the U channel. And the second feature is that this amplitude contains a factor of zeros, which are in the variable U. So let's try to understand why we have these two features. So we first start with the fact that there is no pulse in U. So this part is actually easy to understand. So first on the right, I'm showing you all the relevant component fields that get exchanged in the 4-point function. So each component field can carry a different asymmetry representation. So how is this asymmetry representation captured in the 4-point function? So they are captured by an asymmetry polynomial, which are denoted as y here. So these asymmetry polynomials, they are the eigenfunctions of the two-particle quadratic Casimir of the asymmetry group. So think of those as the analog of the conformal block. So we have a polynomial, asymmetry polynomial for each of the repetitions. And then we can just set sigma equals to 0 and tau equals to 1 to look at what they are in the MRV limit. And we find that all these polynomials in the U channel become 0 in this limit. So that explains why we are not seeing any singularities in the MRV amplitude, because these exchanges are suppressed since their asymmetry polynomials, they vanish in this limit. The second feature is the factor of zeros. The appearance of zeros means that we have some Lang operators with low line twist. They get decoupled in this MRV configuration. Moreover, the location of the zeros should correspond to the conformal twists of the operators which are decoupled. So let me try to explain these 2 points using this simple correlator here. So here I have a table of all the superconformal descendants in a Lang multiplet. So here, in order for all the components to fit into this correlator, the repetition of the superconformal multiplet has to be a superconformal primary has to be a singlet. And we have in total 6 different repetitions. So we can write down the asymmetry polynomials for all of them. And then we take the MRV limit. We find that all the first 5 repetitions, they vanish. And the only one that survives is this 4,0 repetition. So we find a very interesting phenomena that in this MRV limit, the superconformal primary can be absent, but we have some superconformal descendants that are still present. And the guy that survives has a larger conformal twist, which is larger than that of the primary by 4. Now, since we're dealing with some large N theory, so all the Lang operators, we encounter double trace operators. So in this case, the minimal twist is 4 plus 4, so that's 8, but we have just seen that operators with twist 8 should not survive in this limit, and similarly, twist 10 is also absent. So the first thing we are going to see is twist 12. And these numbers, 8 and 10, are precisely these numbers in these zeros. Now, to understand why they are zeros, we need to go back to the definition of Melian amplitude, where we recall we had a product of gamma functions. So in this case, these gamma functions give us double poles because they become squares. So when we have a double pole and when we do the contour integral, we are going to take derivatives, and the derivative can hit on the conformal cross ratios, and that gives us logarithmic singularities. And these the logs, they are associated with enormous dimensions, and and these enormous dimensions, of course, indicating these operators are Lang operators. But we just argued that the twist 8 and the twist 10 Lang operator should decouple. So we must soften these double poles. And to do that, we must need zeros precisely at these locations. And this phenomena is completely general. So in the general case, we are going to have some zeros in U at these locations. So now, so we have understood why we have these 2 interesting features. Now we can actually put them to good use. So these zeros actually, they are highly non-trivial at the level of individual diagrams. And we can use that to fix the contributions from the multiplet. So it turns out that by importing these zeros, we can fix all the relative coefficients of the component fields in the same multiplet. So we can do that in 3 steps. So the first step is that we are going to write down the ansatz, which is just a linear combination of the 6 diagrams. So here, these M's are Melian amplitude for each the diagram of each exchange field. And then these lambdas, there are some coefficients we are not, we didn't fix. Now, in order to impose these zeros, we first need to do something else. So we first need to choose an appropriate contact term in these exchange Witten diagrams. We need to improve its Ricci behavior in the U channel. So this U channel Ricci limit is defined to be s goes to infinity with U fixed. And we need to do that because we can see here that the MRV amplitude has much better Ricci behavior compared to a genetic exchange diagram. And the way to improve the Ricci behavior is very simple. We just need to get rid of this t variable here in terms of s and u, and then discard all the other all the remaining contact terms from this amplitude, and that defines what was called the Polyakov Ricci blocks. So after this, now we can finally impose that we have these zeros in U at each pole, and that turns out to fix all the coefficients in this ansatz up to an overall coefficient. And the remaining parameter, I'm just going to take the lambda for the superconformal primary. But these numbers can be easily computed by just using the known 3-point functions of the superprimaries. So this gives us all the MRV amplitudes as a finite sum over multiplet MRV amplitudes. So this is already quite nice because we can compute all the 4-point correlation functions in a special limit, but we can actually do more. We can even obtain all the four amplitudes from the MRV limit. So here's how it works. So we first start by restoring the dependence in sigma and tau. So we were looking at a special slice of asymmetry. Now we want to look at the general configuration. So this is simple to do. We just need to plug in. So we just need to use these asymmetry polynomials with genetic sigma and tau. We use this exchange contribution from each multiplet in the 4 amplitude, and that fixes all the singular terms, fix all the poles in the amplitude. But there could still be some regular terms which are missed in this procedure. So it turns out that these additional regular terms can be uniquely fixed by imposing superconformal word identities in mailing space. And I should point out here that this division into exchange versus contact is also ambiguous because we can always move some terms from contact into exchange. But the remarkable thing is that we find there's a very natural prescription to complete the MRV amplitudes into 4 amplitudes such that there are no explicit contact terms needed. In other words, the final answer is just going to take the form of just a sum of exchange diagrams with no additional contact terms. The way we arrive at this prescription is to basically just to restore both symmetry. So we notice that in step 1, when we do it like this, we actually have lost both symmetry. So if we interchange particle 1 and 2, we don't get back to the same answer. So to restore that, we notice that actually at each pole, there is a quadratic factor in U, and these coefficients depend on ij, which are the exponents of sigma and tau, and m is an integer that labels the location of the pole, and p is the labels the multiplet. So what we need to do is that we need to get rid of m and trade it for the -1 variable t. And this is possible because we have 2 equations. The first equation is the definition that is the equation that eliminates the redundancy in the parameterization. And the second is that we're looking at a pole at s equals to 2p plus 2m. So we can solve m in terms of t, and then we realize that the answer is now symmetrized with respect to permutation, and we still have the good behavior in the MRV limit. We can do the same thing for the T channel and the U channel, but we can also just get that from the S channel using crossing symmetry. So the upshot of this game is that we now have a full answer for all the amplitudes as a sum over exchange contributions from multiplets labeled by P. And this P is taken from a finite range written here. And it's finite because of two things. The first is that we have asymmetry selection rules at the cubic coupling, and the second is that we need to require that the effective action is finite, which is the same thing as saying the extremal couplings should vanish. And here I want to stress again that there is no additional contact term, and the answer is just the sum of exchange diagrams. So here I demonstrated this construction using the case of ADS7, but it's exactly the same for ADS5 and ADS4. And you can see that is because the multiply structure is the same in all these three cases. So let me now finally present the solution for all these three backgrounds. I'm going to present the solution of the sum over simple poles. So as I already said, it's the sum of S channel plus T channel plus U channel, and each channel has the form of sum over simple poles. We need to figure out, so these residuals come from a finite collection of multiplets labeled by P. And we find in all these three cases, they have a universal structure, which has the form of the product of three things. And these multiplets residuals can be computed in a closed form using the procedure outlined earlier. So this is the final result. So we have K, which is some quadratic polynomial in T and U, and then we have two other factors which involve some gamma functions. So this may look a bit complicated, but all the functions are elementary. And also note here, I wrote the answer as a function of epsilon, where epsilon is related to space dimension. And there are three physical values corresponding to the three backgrounds. And the fact that I can write a single formula for all the three cases indicates that there is quite surprising universality for amplitudes in these different theories. So now let me mention something that's a work in progress. So in the previous slide, we saw the explicit answer for all the correlators, but it's still quite complicated. But if you look a bit closer, we find that there is a very curious hidden structure. So it seems that there is an emergent dimensional reduction of the type of Parisi and Saurus. So what we're going to see is that we start with this background of ADS D plus 1 times SQ. Then we are going to see that the answer can be massaged such that there is a lower dimensional manifold that naturally emerges in the answer, where the ADS part and the S part both have 4 dimensions less. So more precisely, the statement is that we can write the contribution from each multiplet as some differential operator acting on some objects, but that object turns out to be precisely the sum of 3 scalar diagrams in the original ADS background. These scalar diagrams, they have shifted internal dimension. But it turns out that this linear combination miraculously is just a single scalar exchange within diagram. But now in dimensionally reduced ADS space in ADS d-3. And this relation, that equivalence of these three diagrams with this single diagram is because of some dimensional reduction formula associated with the Parisi-Solis supersymmetry. So this is for the ADS part, or the thing that depends on SNC or U. And there's also a completely similar reduction structure for the asymmetry part. So using this observation, we can now rewrite the results in a very simple form. So we find that the amplitude can be just written as the product of 3-point functions times some differential operator acting on a single diagram. So this single diagram is a scalar exchange diagram in some dimensionally reduced ADS space, and then it's multiplied with an asymmetry polynomial that's associated with a dimensionally reduced sphere. So this form of the result seems to suggest that there is some lower dimensional C theory, and the C theory does not have spinning particles. It has only scalars. And that theory is enough to encode all the data for computing the full correlator. Okay, so I guess I'm kind of running out of time. So let me just quickly mention that we can also do an interesting consistency check by going into the flat space limit. So it was pointed out in these papers that a high energy limit of the emitting amplitude, we should just get back the flat space scattering amplitude. And we look at this limit for all the three amplitudes, three families of amplitudes, we find that they always take this universal form. And this is this actually is a consistency check because in flat space at tree level we don't expect to see the dimension of space time. So the fact that we get the same answer is a good thing. Now let me conclude. So in this a constructive derivation for all the tree level correlators in series with maximal superconformal symmetry. We reproduced some bootstrap results already known, and also we give general new results for the other two backgrounds. The crucial observation is that there exists a very nice limit called the MRV limit, where the amplitudes drastically simplify. And these MRV amplitudes, they have very nice features. They don't have poles in the U channels. They have zeros, and also they have improved rigid behavior. And these features allow them to be easily computed. Also, studying this limit reveals that what the underlying organizing principles are for these holographic correlators. It tells that the full correlator can just be reconstructed from this MRV configuration by using symmetries. There's also a very nice feature in these amplitudes, namely that we saw that they can be written just as a sum of exchange diagrams, and there are no additional contact terms. This is a very interesting feature and definitely should be further investigated. It also indicates, this absence of a contact term also indicates that there's certain unsure constructibility. And I should also point out here that this absence of intrinsic contact interaction is also observed at the level of 5-point functions in this paper we put out last year. And finally, let me mention some future directions, which are broadly divided into 3 categories. So the first is we can try to extract data from these amplitudes and try to use them to construct, go to higher genus. So we computed a lot of tree level ADS scattering amplitudes, and by using the ADS CFT correspondence, they encode a lot of both protected and unprotected data about the boundary CFT. So it will be very interesting to extract these states and compare with other methods such as localization and numerical bootstrap. And also these tree-level data, they're essential for using this ADS unitarity method to go from tree level to loop. And this program has been quite advanced for ADS5, but it's just starting for the ADS7 and ADS4 case. The second point is that we can also try to extend this MRV method to both higher points and fewer supercharges. So a good target would be to consider the amplitude of stress tensor multiplets for in the theory of ADS5 and ADS5. And because we're just focusing on the stress tensors, so this is just the same as gauge supergravity. So it'd be nice to extend this notion of MRV to higher points, and those would be the simplest amplitudes to compute. And for theories with, so here I considered theories with 16 supercharges. We can also consider theories with 8 supercharges. And there are a lot of theories with weakly coupled duals. So we also expect there would be new structures that emerge from these theories. Structures emerge in correlators from these theories with half the amount of supersymmetry. The final point is that we should try to explore more analogies with the flux-based amplitudes. So in this talk, we observed there's a very interesting feature, namely the absence of contact terms. So that seems to indicate maybe we will also be able to find an ADS version of BCFW recursion relations in flux-based. More generally, we can try to take some ideas and structures in flux-based and then use that as some inspiration for what we should look for in ADS. And in today's talk, that would be the similarity between MRV and MHV. But of course, in flux-based, there are a lot more interesting things such as color kinematic duality, KLT, or BCJ double copy relations. It'd be very interesting to see if we can find ADS analogs of those objects. And also, it'd be interesting to explore some kind of CHY formalism for these holographic correlators. And there has been some very interesting progress recently by using ambiguous strings. So yeah, so with that, I'm going to stop and invite questions. So thank you very much.
Thank you. Any question from the audience?
Maybe I missed. Okay, go ahead.
You first.
Okay. So maybe you mentioned I missed the you claim that in holography there is a universality like MRV.
Yes.
For different dimensions, but what is the understanding in the CFT data? Purely from considering the conformal field theory, what is the universality there? If you consider different dimensions, this format.
Yeah. So we don't really precisely know what that in terms of like 3-point functions and others. But structurally, well, this is still sort of, well, we can try to understand this kind of from the inversion formula. So the inversion formula has 0 double discontinuity on these double trace operators. So all the contributions are just from the single trace guys. So this fact is true for all these 3 theories. And all these single trace contributions, they are protected. The 3-point functions are protected. So I think this universality can be also explained by using the perspective of Lorentz inversion formula. And also in this case, we have maximal superconformal symmetry, and that means we have better than usual rigid behavior, and that allows us to extend the validity of the inversion formula all the way to negative spins. Because for genetic bolognese CFT, the inversion formula does not converge to scalars.
I see. Another question is, you have ADS P SQ times SQ results, but
yes,
is there any way to, I mean, continue analytic? Is it continue to a Euclidean case? I mean, instead of doing ADS, but you do in hyperbolic space, and
so first of all, the thing I consider here, they are not Lorentzian ADS. They are all these things are Euclidean ADS space.
Oh, so you are actually doing the H space, HP times SQ, right?
Yeah, so it's more convenient to compute things in Euclidean region, and then you can analytically continue to the Lorentzian case. Yeah.
I see. So if that's the case, then we know there is a